Fuel cell. A fuel cell is a device that converts the chemical energy from a fuel into electricity through a chemical reaction with oxygen or another oxidizing agent. Hydrogen is the most common fuel, but hydrocarbons such as natural gas and alcohols like methanol are sometimes used. Fuel cells are different from batteries in that they require a constant source of fuel and oxygen, air to sustain the chemical reaction. They can however produce electricity continually for as long as these inputs are supplied. In 1838, German physicist Christian Friedrich Schonbein invented the first crude fuel cell. A year later, Welsh physicist William Grove developed his first crude fuel cells in 1839. The first commercial use of fuel cells was in NASA space programs to generate power for probes, satellites and space capsules. Since then, fuel cells have been used in many other applications. Fuel cells are used for primary and backup power for commercial, industrial and residential buildings and in remote or inaccessible areas. They are used to power fuel cell vehicles, including automobiles, buses, forklifts, airplanes, boats, motorcycles and submarines. There are many types of fuel cells, but they all consist of an anode negative side, a cathode positive side, and an electrolyte that allows charges to move between the two sides of the fuel cell. Electrons are drawn from the anode to the cathode through an external circuit, producing direct current electricity. As the main difference among fuel cell types is the electrolyte, fuel cells are classified by the type of electrolyte they use. Fuel cells come in a variety of sizes. Individual fuel cells produce relatively small electrical potentials, about 0.7 volts, so cells are stacked, or placed in series, to increase the voltage and meet an application's requirements. In addition to electricity, fuel cells produce water, heat and, depending on the fuel source, very small amounts of nitrogen dioxide and other emissions. The energy efficiency of a fuel cell is generally between 40 to 60%, or up to 85% efficient if waste heat is captured for use. The principle of the fuel cell was discovered by German scientist Christian Friedrich Schonbein in 1838 and published in one of the scientific magazines of the time. Based on this work, the first fuel cell was demonstrated by Welsh scientist and barrister Sir William Robert Grove in the February 1839 edition of the Philosophical Magazine and Journal of Science and later sketched, in 1842, in the same journal. The fuel cell he made used similar materials to today's phosphoric acid fuel cell. In 1939, British engineer Francis Thomas Bacon successfully developed a 5 kW stationary fuel cell. In 1955, W. Thomas Grubb, a chemist working for the General Electric Company (GE), further modified the original fuel cell design by using a sulfonated polystyrene ion exchange membrane as the electrolyte. 3 years later another GE chemist, Leonard Niedrach, devised a way of depositing platinum onto the membrane, which served as catalyst for the necessary hydrogen oxidation and oxygen reduction reactions. This became known as the Grubb-Niedrach fuel cell. GE went on to develop this technology with NASA and McDonnell aircraft, leading to its use during Project Gemini. This was the first commercial use of a fuel cell. In 1959, a team led by Harry Ehrig built a 15 kW fuel cell tractor for Alice Chalmers, which was demonstrated across the U.S. at state fairs. This system used potassium hydroxide as the electrolyte and compressed hydrogen and oxygen as the reactants. Later in 1959, Bacon and his colleagues demonstrated a practical 5 kW unit capable of powering a welding machine. In the 1960s, Pratt & Whitney licensed Bacon's U.S. patents for use in the U.S. space program to supply electricity and drinking water, hydrogen and oxygen being readily available from the spacecraft tanks. In 1991, the first hydrogen fuel cell automobile was developed by Roger Billings. UTC Power was the first company to manufacture and commercialize a large, stationary fuel cell system for use as a cogeneration power plant in hospitals, universities and large office buildings. UTC Power continues to be the sole supplier of fuel cells to NASA for use in space vehicles, having supplied fuel cells for the Apollo missions, and the Space Shuttle program, and is developing fuel cells for cell phone towers and other applications. Types of fuel cells, design. Fuel cells come in many varieties, however, they all work in the same general manner. They are made up of three adjacent segments, the anode, the electrolyte, and the cathode. Two chemical reactions occur at the interfaces of the three different segments. The net result of the two reactions is that fuel is consumed, water or carbon dioxide is created, and an electric current is created, which can be used to power electrical devices, normally referred to as the load. At the anode, a catalyst oxidizes the fuel, usually hydrogen, turning the fuel into a positively charged ion and a negatively charged electron. The electrolyte is a substance specifically designed so ions can pass through it, but the electrons cannot. The freed electrons travel through a wire creating the electric current. The ions travel through the electrolyte to the cathode. Once reaching the cathode, the ions are reunited with the electrons and the two react with a third chemical, usually oxygen, to create water or carbon dioxide. The most important design features in a fuel cell are the electrolyte substance. The electrolyte substance usually defines the type of fuel cell. The fuel that is used. The most common fuel is hydrogen. The anode catalyst breaks down the fuel into electrons and ions. The anode catalyst is usually made up of very fine platinum powder. The cathode catalyst turns the ions into the waste chemicals like water or carbon dioxide. The cathode catalyst is often made up of nickel, but it can also be a nanomaterial-based catalyst. A typical fuel cell produces a voltage from 0.6 volts to 0.7 volts at full rated load. Voltage decreases as current increases, due to several factors. Activation loss. Ohmic loss, voltage drop due to resistance of the cell components and interconnections. Mass transport loss, depletion of reactants at catalyst sites under high loads, causing rapid loss of voltage. To deliver the desired amount of energy, the fuel cells can be combined in series and parallel circuits to yield higher voltage, and parallel channel of configurations allow a higher current to be supplied. Such a design is called a fuel cell stack. The cell surface area can be increased, to allow stronger current from each cell. In the stack, reactant gases must be distributed uniformly over all of the cells to maximize the power output. Proton exchange membrane fuel cells. Construction of a high-temperature PEMFC, bipolar plate as electrode within milled gas channel structure, fabricated from conductive composites, enhanced with graphite, carbon black, carbon fiber, and/or carbon nanotubes for more conductivity, porous carbon papers, reactive layer, usually on the polymer membrane applied, polymer membrane. Condensation of water produced by a PEMFC on the air channel wall. The gold wire around the cell ensures the collection of electric current. Phosphoric acid fuel cell. Phosphoric acid fuel cells (PAFC) were first designed and introduced in 1961 by G. V. Elmore and H. A. Tanner. In these cells, phosphoric acid is used as a non-conductive electrolyte to pass hydrogen-positive ions from the anode to the cathode. These cells commonly work in temperatures of 150 to 200 degrees centigrade. This high temperature will cause heat and energy loss if the heat is not removed and used properly. This heat can be used to produce steam for air conditioning systems or any other thermal energy-consuming system. High-temperature fuel cells. Solid oxide fuel cells (SOFCs) use a solid material, most commonly a ceramic material called YTTRIA stabilized zirconia (YSZ), as the electrolyte. Because SOFCs are made entirely of solid materials, they are not limited to the flat plane configuration of other types of fuel cells and are often designed as rolled tubes. They require high operating temperatures 800 to 1000 degrees Celsius and can be run on a variety of fuels including natural gas. SOFCs are unique in that negatively charged oxygen ions travel from the cathode negative side of the fuel cell to the anode positive side of the fuel cell, instead of positively charged hydrogen ions traveling from the anode to the cathode, as is the case in all other types of fuel cells. Oxygen gas is fed through the cathode, where it reacts with electrons to create oxygen ions. The oxygen ions then travel through the electrolyte to react with hydrogen gas at the anode. The reaction at the anode produces electricity and water as byproducts. Carbon dioxide may also be a byproduct depending on the fuel, but the carbon emissions from an SOFC system are less than those from a fossil fuel combustion plant. Molten carbonate fuel cells (MCFCs) require a high operating temperature, 650 degrees Celsius (1200 degrees Fahrenheit), similar to SOFCs. MCFCs use lithium potassium carbonate salt as an electrolyte, and this salt liquefies at high temperatures, allowing for the movement of charge within the cell, in this case, negative carbonate ions. Like SOFCs, MCFCs are capable of converting fossil fuel to a hydrogen-rich gas in the anode, eliminating the need to produce hydrogen externally. The reforming process creates CO2 emissions. MCFC-compatible fuels include natural gas, biogas and gas produced from coal. The hydrogen in the gas reacts with carbonate ions from the electrolyte to produce water, carbon dioxide, electrons and small amounts of other chemicals. The electrons travel through an external circuit creating electricity and return to the cathode. There, oxygen from the air and carbon dioxide recycled from the anode react with the electrons to form carbonate ions that replenish the electrolyte, completing the circuit. Applications: Type 212 submarine with fuel cell propulsion of the German Navy in dry dock. Fuel cell electric vehicles. Hydrogen fueling station. Research and development.